Well, hello everyone. Hello students. Hope you are very, very well and you are really enjoying the session, the subject and everything. First of all, do you have any questions? Do you have something? Would you like to comment or something? No, no. Okay, then let's go. Last class we saw the quantum phase estimation algorithm, okay, where we saw that it's a non-practical algorithm because it's too deep and it requires a lot of qubits to really being able to execute it and get the advantage. But on the opposite, but on the opposite, it is a theoretical quantum algorithm that is demonstrated that it has an advantage against its classical counterpart. So it's good to take into consideration as well as that it is good to consider. Okay. With that said, let's go for today, class. Today we are going to see mainly the Grover algorithm and maybe some of its applications. Okay. And we will also see in a high level the HHL algorithm as well. Okay. Okay. I think you see both algorithms in the quantum algorithms class, correct?
Yes.
Okay. What can you tell me about them? Can you tell me something about them? Do you want to tell me something about them or no? No problem at all if you don't want. No? You cannot tell me anything?
Well, the Grover is a search algorithm, right?
But
And AUGL is to solve linear equations in a very high
very
level.
good. Very good, very good. Important one, I mean, in a high level, it's correct. Both are correct. I would add one very important word. I would say I would add in Grover is a search algorithm inside unstructured data. Okay, it's not the in relation data or structured data. Why? Because for that we have SQL, server query language, that is so powerful and everybody uses in business. And I mean, well, and we also have classical algorithms to do in unstructured data, but it's important to highlight that Grover is for unstructured data, not a structured data. Okay. Okay, cool. And the HHL, yeah, linear systems of equations, diagonalization of a matrix that is based on linear systems of equations is based in a lot of very complicated algorithm. Basically in aerospace, because solving the Bernoulli equations and all of these equations take its time and all of these are linear equations. Okay. So basically are used in this type of problems of linear equations that is how to solve the dynamics of movement of the space, basically, of the satellites when they are sent to the space, or oh shit, I don't know how to say now. The oh, the airplanes. Sorry, I would not even forget. So how the airplanes can fly in a better way or something, but it is used as well in other areas, like for example in the oil and gas company on how to move forward the bitumen from one place to another. But as this is a very very difficult component, all of these HHL algorithms, and it increases very exponentially with everything, and to solve it is very difficult. In aerospace they cannot, but for example in the oil and gas on how to transport bitumen, it's working another way, that is by the heat, by the temperature, because if the bitumen is the blend, okay, if the bitumen is more hot, it lose viscosity and it can be transported in a easier way rather than if it's cold where the viscosity is high. Okay, because the main problem for the bitumen, the blend, the gas oil, for the blend is that you extract this in some place, but then the factory where you do all the blending process to finally to get the final product for the refineries is done long way ago. I mean, in long way, in long distances. For example, in Canada is a very important fact. So that's why it's important on how to transport it in an effective and efficient way. But this will not be, I would say, in the following years, not a problem anymore because we have the electrical vehicle. But I think we still have a lot of time to go there. Okay. Okay, cool. Let's go for it. And what I need to do. Okay. 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 Mhm. Okay, cool. Let's start. I'm going to start sharing my screen. Please let me know when you can see it. Can you see the screen?
Yes.
Cool. Thank you very much. Okay, then we are going to explain the Grover algorithm in very simplified way. Okay, just to that we are all aligned, and in case you didn't understand it, but I'm sure that you understood it. But let me. Okay. Grover's algorithm. What does it does? The Grover algorithm. The Grover algorithm, firstly, it's very important as always to highlight that the Grover's algorithm is a theoretical quantum algorithm. Remember, in my vocabulary, a theoretical quantum algorithm is the one that is demonstrating theoretically to have an advantage against its classical counterpart. For example, here we can see that the Grover's algorithm have a quadratic speedup against a classical algorithm. Okay, because of this symbol. So, the Grover's algorithm is a theoretical quantum algorithm used for a searcher in an unstructured database on an unstructured search. What does it mean? How would work the Grover's algorithm in the real life? Imagine that we have a box. Well, 1 second. I'm going to open the lights. Okay, cool. Then, how the Grover's algorithm would work in the real life? Imagine that we have a box. Okay, we have a box with four balls. Blue ball, red ball, green ball, and white ball. Okay, this is an unstructured database. Well, in that case, these four balls are labels with the color. Okay, but this is an structured database because we don't know. I mean, imagine that these balls are not labeled. Okay, imagine that is maybe one, two, three, and we want to get the third, whatever. But how this would work is, and they are not structured, okay? It's like in machine learning is unsupervised learning. That's why it's unstructured search, okay? So all of these are not labeled. And what do? We do is imagine a box. We have four balls, red, blue, white, and dark. I'm going to put red. Well, this is Barca's colors. I don't like Barca. Then Real Madrid, purple, white, and then green and dark. Purple, white, green, and dark. Okay, so imagine we have four balls, and we have a box. So how the Roberts algorithm would work is we include these four balls in the box, and we have it. Now we execute the Grover algorithm. Shaking the box is executing the Grover algorithm. Okay, shaking the box. And imagine that we insert the balls and we don't shake, but we say, okay, I want to extract the green ball. So I shake, I compute, I execute the Grover algorithm, I shake. Once it's finished, I open the ball, I insert the hand with no seeing because the balls are not labeled. Okay, I say green, etc., just to emphasize to see how it works, but they are not labeled. So I include the hand, and when I touch, I see that three balls are like this. The size decreases a lot. The size decreased a lot, while there is one ball that the size increased a lot. So I get the ball, and if I extract the biggest ball, it would be the green ball. Okay, and this is how the Grover's algorithm works. We have four balls, we include them in the box, we shake the box, we execute the Grover algorithm, and then it changes the size. When we include the hand, we extract the biggest ball, that is the ball that we were looking for, that is the green ball. Okay, this is how the Grover algorithm would work, and as I said, this is a theoretical quantum algorithm that has an advantage against its classical counterpart, as you can see here. So, how it works? Basically, the Grover algorithm, we just have one target qubit, okay, where this target qubit contains all the registers, contains all the states and registers. So, first, we initialize the system, as always, all the Hadamars to all the qubits. Secondly, we apply the oracle. The oracle is basically to detect to no how to say to put in the circuit what is the element that we are looking for. Okay, meaning that we are looking for the element number three, for example, as I said, the green ball. Okay, so we are highlighting in the circuit that we are looking for this element, and this is the oracle. We will see afterwards, and you probably already know that this is changing the sign of this element. And then afterward, we use the diffusion operator, what is called the diffusion operator. The diffusion operator is applying an oracle, of course, with the Hadamard's, etc. The diffusion operator is applying an oracle where we are doubling the size of the selected element. It's what I said, right? I mean, we have a box, we include the four balls. We want to extract the green ball, that is the selected element green ball. We shake the Grover's algorithm, we execute of this part of the Grover's algorithm, and the green ball, the selected element, the green ball increases the size by the diffusion operator, and when we measure, we get the green ball. Okay? So, am I going fast or is it fine? Because I know I speak very fast sometimes or almost always, and I think it's good for you, or should I go slower?
I think it's fine. Thank
Okay.
you.
As always, please, anytime you want, and I cannot see your faces because I really would like to see your faces, but as I cannot see your faces, please, anytime you want, just interrupt me, okay? Then we have this, okay? Then we execute, then, as I said, we initialize, we put all the balls into the box. We put the oracle function, means that we change the sign of the selected element. We apply the diffusion operator. What it means is that we increases the size considerably of the decided element, as well as we also change the size of the amplitude. Okay, and we finally measure it, and we get the desired element. Oh, very good. We win. Okay, I'm going to be fast, but yeah. And this is how the quantum circuit looks like. But I don't know why we have this here. Okay, I think this is having here because I didn't forget that. I mean, the most important part is right there. I'm showing this image because of this. I don't remember now what we have here, a target QBD controller. I mean, this is an oracle. You can forget about this because the oracle can be used here, just not a problem because here face feedback. But this is important. The diffusion operator was very well studied. Okay, the diffusion operator was very well studied that it has this form. Hadamard's, it belongs to this, but all of this diffusion operator is basically big flip gate, Hadamard gate, and then a super, well, not super, but multi-control C not gate, multi C not gate, multi-control gate, a CX gate that is applied to all the qubits till the last one. So for example, if we have two qubits, just two qubits, it will be a CNOT gate if we have four elements, but if we have eight elements, three qubits, we have a Toffoli gate right here, okay? That we, of course, this multi-control gate, we need to decompose in elementary gates that can be applied to the quantum computer, but this is as it is, okay? Then we have the Hadamard, the bit flip, and finally Hadamard, that this is the initialization right here as well. But the diffusion operator is this part over here, the bit flip, with this that is called the conditional phase shift, that all of this is the diffusion operator. Okay? Questions? Please? No? Cool. Then now I'm going to explain. One of the one of the applications that can be done for the Grover's algorithm. Another application is for optimization problems, where you will be able to see that. Okay? For optimization problems, where you will be able to see that in the Jupyter notebook that I will show after this. But then here we have the quantum associative memory. Okay, what is a quantum associative memory? If we have a standard memory, we have a structured data, okay? We have structured data and we input the label of the data, okay? We input we input the label of the data, we input the cell of the data we want to extract, for example, in that case, 10, and we get a cut. But how does associated memory works? Well, if I tell you physicist, Austrian, physicist, Austrian, eh, general relativity, photoelectric effect, what would you tell me, please?
Einstein.
Einstein?
Correct. So this is correct. Thank you very much. So this is how an associative memory works. It does not, I mean, with all of this, I didn't tell you, I mean, I didn't give you a data set where one is Nikola Tesla, second is Michael Faraday, and third is Albert Einstein, and I tell you Albert Einstein. No, what I tell you is different components of it. You associate this information and you extract the value. I told you different features of the data I want to extract, and you gave me the value. So an associative memory works very similar to a brain. You give information for unstructured data and then you extract the data. In that case, it, I mean, this is how it works. So, in that case, for example, in a computer, how an associative memory works is that you give certain part of the solution and then you get the output. For example, imagine that rather than having, I mean, for example, the example that we have here is we give to the computer the tails and the nail of a cat, and then it gives us the final image of the cat because we were giving the pixels. So we associate, and it can associate for the rest to complete all the image because the rest of images has not the same figure, you know. As we're going to see now, another example would be, imagine that we have, as I said, Nikola Tesla, Albert Einstein, and Michael Faraday. If I give Michael to the associative memory, I'm going to get Michael Faraday. If I give Albert, I'm going to get Albert Einstein. But imagine that instead of this, we have Nikola Tesla, Albert Einstein, Michael Faraday, and I don't know, Michael Ulrich, I don't know, Michael Garcia, I'm going to put my surname, Michael Garcia. If we give to the associative memory Michael, it will give us both solutions, Michael Garcia and Michael Faraday. Why? Because it's an associative. We are giving them a relationship between the outcome, etc. We are giving them the input, and it gives us all what we are associating in the unstructured data. Okay? Then, why is this used for? Basically, I'm going to start for the worst one. Artificial intelligence, smart control for robotics, like reinforcement learning, something like that, meaning that the robot starts with a movement, so it uses associative memory to recognize what is the movement that it needs to take. And basically, what is used today in business is image recognition and voice recognition, because you need to imagine that we have a lot of things. Now we have Gen AI, of course, okay? So associative memory is a discriminative AI, but we also have now generative AI, so it's different. Maybe there are other use cases that accelerate past behaviors, okay? But for image recognition, it's the same that we did here. We have different pixels in the image, so we fill it down to finally have the face we want, for example, or voice recognition, we say a word, or the example I put, Michael Faraday or Michael Garcia. So this is the same. We put a name that we want to find because it's a thief or something, a thief, and we want to find it, and we need to an associative memory to allocate that to the other. Okay? Then, how it works and how are we going to see here in the Grover algorithm? In the same way, but rather than with voices or images, with binary numbers, because it's the way on how to encode in qubits. Of course, remember what I told you last lesson. All computing needs a pre-processing and a post-processing of the information. Even in classical computing, every pixel of the image has a number of bits associated to that. So this is just the simplest and the most easiest step. But with this, we could encode definitely we could encode an image. Okay, we are just giving the simple state because this is what we are doing here. But imagine a lot of layers in the architecture that this, for example, pixel corresponds to one tail of the cat. This other binary number corresponds to the other tail of the cat. And thanks to that and encoding layer, abstract layer, we can encode the full image. But here, just for learning and teaching purposes, we are giving just a simple example. But in real life, everything works like that. It's just that working step by step on that and going forward. Okay, so how are we going to work here? We have an associative memory. Then in this associative memory, we have different elements that we put right here. And finally, we give them an input that is something we want to restore. We put the input of 0, 0, 5, for example, 0, 0, 0, 1, and we told the associative memory, we shake the hand. What is this number? What is this pixel associated? The nail of the tail or the head of the cat? And it tells us, this is the tail of the cat. Okay? And this is how an associative memory works. Very similar for a Hopfield network. It's a neural network with just one neuron. Okay? No, sorry, one neuron, no, one layer. Do you know something about neural networks, etc., or not? Should I explain something to give you more context here or not? I mean, we will see that in detail in quantum machine learning, but just in case you don't understand that. You understand? I mean, I think Raúl and Urbano, you have context, but do you have as well, Marta?
A little bit.
Okay, very simplistically, let me show you the difference because as you told me that you're working in cybersecurity, that's why I was wondering whether you have it or not. Okay. Mm, Usually in neural networks, what you do with all the providers, etc., what you do is you build layers of neurons. Every layer can have thousands of neurons or whatever. Deep learning is having a lot of thousands or if not million, but thousands of layers, even million of layers, one upon the other, and every layer has multiple neurons. Okay, so this is, for example, a neural network with 4 layers and 11 neurons. Okay, here a Hopfield network is a monolayer network. Okay, and it's used for unstructured data for non-supervised learning. Okay, so that's why it's very similar to a associative memory. And this is the classical associative memory, the easiest, I would say, was one of the main applications of AI. Okay, and that's it, I would say. I mean, for the explanation, right? Mhm. Okay, so one of the main applications at the very beginning of the Grover algorithm is the quantum associative memory. Of course, we need to modify it so we can use it appropriately. But what do? We have a first circuit, an oracle, to build the circuit, to build all of these states. We create an oracle where we can create all of these states. Okay, we saw that in the first class I did, that was 4 classes ago. If you want me to refresh something, please let me know. But we can create an oracle here to do this, to prepare this. Okay. Then, secondly, we have the recovery the information. We use a modified Grover. It's quite very similar, but it's just a modified Grover to be enabled to do the associative memory. And finally, we measure. And we have different ones, etc. And then you execute it, and then you get the right answer. Okay, now we're going to see better in a Jupyter notebook. Okay, with that said, questions, please? Is there any question? Am I going very fast? I'm going fast because I need to leave, as I said, 5 minutes earlier from 8, and I want you to program a bit today in class with some other stuff. Okay, till now, is this fine? Should I repeat anything? Or am I going very fast? Please answer.
It's okay.
No. Yeah, I think it's okay too.
Okay,
I was just wondering, I mean, if I can ask a question, I was just wondering, I mean,
all questions you want.
uh, I think I may be missing the link between Grover and quantum, and I mean, or is that's the next step we're gonna go to? Sorry.
Can you repeat the question? Sorry, Urbano.
No, I was just trying to understand, I mean, where Grover enters in all of this. I mean, that's what I was trying to understand.
Grover
I
is
mean, I
what?
understand the concept that you just showed us the circuit at the end, which you have this Grover part, but basically, I mean, uh, the way Grover's works there is because it kind of find these patterns on the associative memory. Is that right?
I mean, Grover's is the quantum associative memory. I mean, the Grover's algorithm is used for a quantum associative memory. I mean, you use Grover to find the patterns inside the unstructured data. I mean, here you have all of this data that is not labeled, and in classical you would use a Hopfield network. But in quantum, you use the Grover algorithm to solve that problem. Imagine that what I say, the examples of Michael Faraday, etc., or the example of the image. Here, for example, you are using the Grover algorithm to get the final cat image. Or you use the Grover algorithm to get Michael Garcia and Michael Faraday. Grover is is a quantum associative memory.
Okay. Okay, I see. So basically what you're saying is that when we prepare the oracle, what we're doing in a way is giving the Michael part, right? Of the Michael Jordan or Michael Garcia, sorry.
I mean, correct. I mean, just repeating that so it's clear. I put Michael and the Grover algorithm give me Garcia, and I put Michael and the Grover algorithm gives me Garcia and Faraday.
I see. I see. Thank you.
I mean, the Grover's one of the applications of the Grover algorithm is being a quantum associative memory. It can work as a quantum associative memory, but this is one of the applications of the Grover algorithm because, as we are going to see now, the Grover algorithm can also work as an optimizer. It's not useful at all. It's much better adiabatic quantum computing today, but it can also be used as an optimizer. Okay.
Okay.
Yeah, yeah.
Thanks.
Thank you very much, Urbano. I mean, please ask all questions you want.
Berto, and then another question.
Yeah, yeah,
Um,
please. I like
when
it.
do the networks come in?
What?
Like we have, when do the networks that you explained, the neuronal things,
Hmm.
play a role? Like you have this associative memory based on the Grover's algorithm, and how do the networks play a role or
Okay,
come in?
I'm not speaking very fast, but I'm not explaining myself correctly. Thank you very much, Marta, for what I see. Sorry for that, students. Okay, I need to clarify three different elements in this, okay? I mean, I think you know all the information, but I need to clarify the definitions. One, use case is a problem, a business problem, okay? And quantum associative memory is an application. Grover is an algorithm, and associative memory is an application. What does it mean? And then this is in a database. What does it mean? Here, for example, in the vocabulary is database, we insert an input, we execute the Grover algorithm, and we get the output. Michael, Grover algorithm, Faraday Garcia. But I can also say database input Michael, I execute the associative memory and I get the output Garcia and Faraday. I mean, Grover algorithm is theoretical, and then the Grover algorithm can be applied as an optimizer, an associative memory, a pattern recognition, etc. Meaning that Grover algorithm can have multiple use cases, can have multiple usages. Does this now make sense, Marta?
Yes.
No. For your
Yes,
answer, I
yes, I
think no.
understand. It's just I don't know the networks, the neuronal networks. When
Mhm.
do we use them here?
Yeah. Okay. We have the data. You understand that? Okay. So you apply dataset, and then we execute a Hopfield network, a neural network, or a Grover algorithm, and we get the output. And all of these in that use case, in that problem, are applied as an associative memory. A neural network could be another element that could be acting as an associative memory.
Ah, okay. Okay, so it's like the classical counterpart, or it can also be included in hybrid things.
Correct, perfectly. Yeah, I'm happy now.
Okay.
I explained myself correctly. Yeah.
Thank you, Alberto.
No, 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 please, please. I
Detail.
mean, if I'm going, no, I see now that I'm going very fast and I'm giving all the information, but not well structured. So sorry, students. It's my fault. But yeah, this is exactly what you said, Marta. Thank you very much for asking. And please ask whenever you want, because if you don't say anything, I think you understand, and this is important. Cool. More things? No? Okay. Then let's go. Let's go for the class. Okay. Please, my recommendation now is that you start a Jupyter notebook. I would like from you today to program a bit, please, and copy this, please, and let me know when you finish. I give you 3 minutes, maybe a bit more, but I know that you need to start everything, you need to do everything, so that's why I give you time. But please open a Jupyter notebook, and I really would like to do that. If none of you are going to do that, please let me know as well, so we don't waste time. But for me, it would be very good if you can program today.
Blank notebook, it's okay, Alberto, or should we open a specific one?
No, blank notebook, yes. Did you install Qiskit?
Yes.
Okay, cool. Then yes, a damn notebook. Anything, a white, I mean blank. Yeah, yeah, yeah. I mean, I don't want you to. I want you to program today, nothing else. So copy all of this, please.
Alberto, which Qiskit optimization are you using? I'm trying to import the Grover optimizer, but it doesn't recognize the Qiskit optimization dot algorithms.
You need to install pip Qiskit optimization. Did you do that?
Oops.
Or
Yeah, I
Qiskit?
did. Oh, maybe no, maybe I did something wrong here. Sorry.
No problem. But you need
Yeah,
to.
no, now it runs. Yeah, no, now it runs. Now it runs. Yeah, no, it was a typo. Sorry.
No, no, no problem. I mean, basically, being very honest, Urbano, I know that this is correct, not only because I review it last days, it's because I renew my Mac in
You just
work.
installed everything again.
Correct. So I know this is
I
the
say, yeah.
first. Yeah, correct. I mean,
No, it's just that I mean, Qiskit changes so much that
yeah.
is just like,
Yeah, yeah. I mean, well, a very good comment because Marta, you see, he did not weather establish at all. But yeah, I mean, that's why I know this is good. I mean, and this is correct. Basically, because yeah, I renew my Mac and I install everything from scratch like 1 week ago or 2 weeks ago because I renew it. So
yeah, I think we were missing the Qiskit algorithms and the Qiskit optimization there because I created an
this,
environment with the requirements that you guys put out there.
yeah, but the problem
But
is,
I think it was missing the algorithms and the optimization. Yeah.
yeah, it is, yeah, because it was from
Thank
Alejandro's
you.
part and not mine. Yeah, I need to sync with.
I see.
The same that I told Alejandro
No.
yesterday to upload the deliverables, okay? And he told me he's going to do on the weekend.
Mm, Okay. Thank you.
Did you finish? Or are you on the way?
On the way,
Okay.
getting problems with the algorithm module. I don't know
Which
if
one?
I have installed it. The one Qiskit algorithms.
This is important.
Yeah.
Okay. I mean, if you want to share the screen, we can take a look if you want, Marta.
Okay, let me see if it is installing something. I'm ready now.
Good. Urbano, Raúl, are you ready? Urbano, Raúl.
Almost.
Okay. Raúl, are you ready? Because I think I'm
Yeah.
not. You're ready? Okay, cool. Then I think I'm going to start, okay, Urbano? You continue. I mean, now I'm going to explain
All
the.
right. Yeah, it's ready here too. Thank you.
Okay, cool. Then let's go for it. Okay, cool. Then now what we are going to see is basically how the Grover's algorithm work in a more detail. I want you to do very few things, okay? Just so you start practicing it. And then what I really want you to do is from the Grover optimizer, an application with the Grover algorithm. We will do a very simplified one and it will be very easy, no worries. Okay, then we go for the Grover algorithm. As I said, I already explained that. We initialize the system, we input an oracle, that the oracle is basically selecting the quantum algorithm, that what it does, the oracle, is changing the amplitude, changing the amplitude of the selected element, of the selected, yeah, of the selecting element, okay? And then we do an amplification algorithm that basically the amplification algorithm, the diffusion operator, the control phase shift operator, I mean, it has multiple names, the Grover diffusion operator, etc., is basically that it increases the size of the selected algorithm to get finally the final outcome of the unstructured database. Okay? So now what we are going to do is to perform the Grover algorithm for we are going to execute the Grover algorithm to get two different outcomes, Michael Faraday and Michael Garcia. Okay? We are going to put three qubits. This oracle is very simple, very, very simple. That's why I didn't remember why it shows. Did you remember the image that I showed previously? With the organic search of the Grover algorithm that puts a control qubit in the oracle? Did you remember this part?
Yes.
This not this one, the other one. This one. That here there is a control one. I don't remember being very honest why it said that, but it's not important because basically the Grover algorithm, the oracle of the Grover algorithm is that simple. I mean, at the end, we have multiple elements we want to search, we have anything we want or whatever, and we just need to have this minus one, minus one. Moreover, at the very beginning, when we started doing this Grover algorithm, okay, at the very beginning, it was tricky because we needed to have the shallowest. Well, it's still tricky, but we already have some tools. But at the very beginning, we didn't have any tools, so it was very tricky to get the shallowest circuit where this can be executed. In fact, there was a challenge from IBM when I started, like maybe 7 years ago, 6, 7 years ago, that one Spanish won from Spain, that it was based on a matrix, what is the shallowest circuit that you can obtain. Of course, it was very theoretical because you can do that, etc. And the key fact of this matrix that was shown, the key fact where this student from Spain, from the CSIC, won is because he saw that the matrix could be diagonalized, and a diagonalized matrix is not only much simple to translate in a quantum circuit, but also with much more with much less gates than a matrix not non-diagonalized. I think it's clear because if it's not clear for you, not a problem, Ari will explain. But basically, here we just have elements of the diagonal based, where in the non-diagonal we have none. So we just need to take care of this. If we have two elements here, this is a connection between elements, okay? How you need to imagine this is imagine that these are, well, imagine no, these are the qubits that are interacting here, right? So how this is expressed into matrices, I mean, I don't have a clear idea. It's very difficult. As you know, it's a scientific paper entirely, and there is a specific tool that IBM developed for us. But basically, more or less, what you need to imagine, if we have a diagonal, we do have we do not have two different qubits connected to each other. But if we have here one, it means that qubit one, two, three, four. Well, I'm going to put this one to be simple. One, two. Qubit 2 with qubit 3 is connected somehow. There is a connection in the non-diagonal element. So this is what it really, I mean, damage the circuit, okay, the non-diagonal elements. So what I try to say is this oracle in the Grover algorithm is very, very simple because it can be as large as we want. That's not a problem, but it is going to be always in the same way. Where where we see the selected element we want is where we are going to put a -1. That's it, nothing else. It can be super large and it's going to be diagonal, so it's not tricky. When we can use the how to construct an oracle of the first class, that is a tool that Qiskit allows us to build such matrix. Then we do that and we initialize the system and then we start building. And now, okay, once we have this, we selected the two different elements and we start building it. Okay, this is a very important question. Do you see why these elements is this over 2 here? Do I need to explain why or is it clear? Okay, no one answers, so I understand. Is it clear? Raul, I'm sorry, I'm a bad professor right now. Raul, can you explain this, please? Or you don't want to speak? Raul?
Explain why the 101 is part of the matrix.
Yes.
Um, because of the
No,
tensors.
I mean, no. 101 is part of the matrix? No, sorry, no. Why 10? I mean, do you know how to order the different elements in the matrix already?
Because of the tensors, right? Of the
No, but
operations.
okay, I'm going to try. Okay, sorry, I'm going to explain myself better. Um, what this column corresponds to? Which what this column corresponds to for the in the we have three qubits in the matrix in the circuit, okay? And we then as we have three qubits, we have 2 to the 3, so 8 elements. So what is this column? What is the element that corresponds to this column? Do you know the answer to this question? I mean, it's a tricky question, but I mean, it's very simple, it's true, but it's a tricky question, I know. That's why I'm asking you, because I want you to have this clear. Do you know,
Is that the
Raul?
010?
No. Okay, no problem. But I'm going to explain. This is very important. Qiskit and everybody, how we order the matrices is ascending order based on binary numbers. 0, 1, 2, 3, 4, 5, 6, 7. This is 8 elements for a 3 qubit circuit. If we have 4 qubits, we will have a 16 multiplied by 16 elements in the matrix, 16 rows and 16 columns. If we have 5 qubits, we will have 32 columns and 32 rows. So the way how this is ordered is 0, 1, 2, 3, 4, 5, 6, 7, 0, 1, 2, 3, 4, 5, 6, 7. But when we order with qubits, qubits is quantum bit. Bit it's only 0 or 1. So we don't need to put decimal numbers here. We can put decimal numbers, but we need to understand that this is always binary. So it's 0, 0, 0, 0, 0, 1. 0 1 0 0 1 1
Yeah.
1 0 0 1 0 1 1 1 0 1 1 0 and finally 1 1 1. Maybe I didn't express my question correctly, okay? But what I wanted to say, what I wanted you to ask is why is this? Because it's ordered in ascending order and this is the position it takes for this number. Sorry
Okay.
if I didn't ask correctly, Raul, for that. Sorry.
And
But
so the answer is because of ascending order.
yeah, I mean, the only thing that I want you to be aware is that the order. Of course, I mean, because in mathematics, in physics, you can take the reference, the inertial system that you want. Meaning that, imagine that you want to order this like 0 0 1 1 1 1 1 0 1 0 1 blah, 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 and so on and so forth. Okay, you could order this because it's your inertial system, it's your system of reference, so it wouldn't be a problem. if your reference system. But in quantum computing, for you to know, in quantum computing for all the providers, it is established that, of course, for a tensor network, for a multiplication of a tensor network, definitely, but basically it's order in ascending order of decimal numbers 0, 1, 2, 3, 4, 5, 7. So it's 0, 0, 0, 0, 1, 0, 1, 0, 0, 1, 1, 1, 0, 0, 1, 1, 0, 1, 1, 1, 0, and 1, 1, 1. So it's the binary numbers of the ascending order or decimal. Do you
Okay.
get my point?
Yes. Yes. Thank you.
So if I tell you now, instead of 1, 0, 1, 1, 1, 0, if I tell you 0, 1, 1, you need to go 0, 0, 0, 0, 0, 1, 0, 1, 0, 0, 1, 1. So it should be the minus here. Okay? And then
Okay.
thank you, Raul, for replying. But yeah, I mean, so I want you to be aware of it because it's important. It's the same like in the previous was we were commenting. The order on how the qubits are expressed. Here, the qubits are expressed in the circuit and how the qubits are expressed in the matrix and how the qubits are expressed in the outcome, in the plot of the counts. Okay, for example, this is qubit 0, this is qubit 1, and this is qubit 2. Why? Because if we want to translate this number in a binary number, remember, do you want me to write it? First question, apart from it, do you want me to write it when I'm explaining, or it is not necessary?
Maybe the first one, yes.
Okay, cool. Thank you, Marta. No, because I'm going very fast and I don't want to go fast. That's why I'm saying all of this. And you need to interrupt me because I know that sometimes I speak very, very fast. I mean, I completely understand. My brother speaks even faster than me, so imagine. He's the only person I cannot put in 1.5 or 2 or 2 times faster in WhatsApp. My brother, so imagine. Okay, did you understand how it's ordered in the matrix, right? So we have now here, for example, 101. Have here 101. Then this is qubit 0, qubit 1, and qubit 2. Okay. So this we would say in the matrix you have 0, 0, 1, minus 1, 0. It is 0, 0, 0. This is 0, 0, 1. This is 1, 0, 1, 1, 1, 1. So we do this, we go here, we put matrix is ordered by ascending order of decimal binary. Okay? And then here, this is qubit 0. We start from the left because if we want to express this with a decimal, how it is translating is 1 multiplied by 2 to 0, 1, 2 plus. Imagine, remember we need always to pass from decimal to binary and binary decimal. 0 multiplied to 2 to 1 plus 1 multiplied to 2 to 0. So what we get is 4 plus 0 plus 1, 5. That's why this is qubit 0, because it corresponds to 0. And then this is when we have 3 qubit 0, qubit 1, and qubit 2. Here, if we want to express this 1, 0, 1, what should we do? X here, right? Because it's qubit 0. No, this is 0, 0, 0, sorry. here nothing, and here x, and we finally get 1, 0, 1. And if we go to a plot, then we will have, for example, 1000 counts, and we would have here 1, 0, 1, that this is the same. 1 qubit 2, 0 qubit 1, and 1 qubit 0. Okay? I'm sorry, I need to go for my resin glasses. Okay? So, do you understand now what I mean? I mean, I know this is very simple, and this I would say even the physicist teacher said is trivial, but it's tricky because if you don't know how to read everything, it's tricky. So here, when you come here, you need to know how to read that, as well as here you need to express to put that here, you know? So in this circuit, I put XX because this is the way on how to get from 0, 0, 0 to 1, 0, 1. But in that case, we cannot put that. Why? Because we need to fulfill the order of the, we need to fulfill the order of the, and here there is also control qubit. Maybe it's because it's simple. But here we need to fulfill the order of the Grover algorithm. Okay? Now is it, I mean, do you understand now what I mean?
Yes.
Yeah.
Yes.
Okay,
Yeah.
cool. Thank you very much for replying. Okay, so then what we do now is that we create a circuit where we have qubit 0, qubit 1, and qubit 2. We initialize the system, and then what we have here is the oracle that we apply. Okay? Then what do we apply here? Let me see this. Mm, And now, what do we apply here? What we do apply is this. What can we see here? That this is qubit 0 and this is qubit n, right? Because the C not gate is applied in the qubit 0, while here, I will save it that for while here, this is applied up the top, okay? And this is not the C not gate, it's this gate. I was wrong, sorry for that. Okay, and the way to express that, as you can see, it always feels the same structure. Hadamard, the amplification, the diffusion operator always see the same order. Hadamard, X, multi-control gate with Z, X, and Hadamard. If we have 4 qubits, the same. Another qubit, another control here, X, X, H. 5, the same, and so on and so forth. And this is the structure that was seen and understood for the diffusion operator to be universal and general, theoretical. I suppose it was theoretical demonstrated. Okay, so we will go with the amplification and we put right here. Okay, and then we get here the same structure. Initialization, the oracle, the diffusion operator, and finally we measure it. As you can see, diffusion operator, this is not respected the, I would say not, it's not that not respected the order, but is one upon another because it always tries to put the minimal one. I will explain now why. But we have the Hadamard, the X, H Hadamard, then the multi-control gate, and finally again the X, the Hadamard, and the H. Why it does not respect the case? Because in that case, the circuit depth has 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 10 layers. Okay, I don't know if it was called layers or something. I think so, it's layers, but this is why it's included here because if it could be here, because it's here, so but it's 10 layers, and this is very important because it's one of the ways to measure the circuit depth. Okay, the quantum circuit depth is such this. 1, 2, 3. I mean, you count the layers based on the gates that are in every qubit, so you count them to count the circuit depth, and is one of the metrics that are usually used to count the circuit depth. Not only the number of gates, but also the layers that the circuit has, the quantum circuit has. Okay? Then we apply it, and finally we get the counts, and the result is the expected 101, 110. Okay? What time is it? Okay, cool. Okay? Then I'm not going to put you to write this. No worries. This is not encapsulated, so you see how it works. Of course, another fact is that before I put all of this, you could use the decompose. You could use the decompose function, so you can decompose this into elementary gates, because it's true that these are almost elementary gates, but the multi-control gate and these two control gates are not elementary gates. So this would be the compose. So the real quantum circuit that would be executed in a real quantum computer is much, much, much deep and larger than this one over here. Okay? You always need to remember that. I mean, we can see everything. Everything in computing is one encapsulating into another, and this is the key fact. When you see an image, it's thousands of bits, etc. Okay, awesome. So in quantum computing is the same. So you can imagine how far we are when the real quantum computer as of today, I would say that can only execute properly 3 qubits and 3 maximum 4 layer of a quantum circuit. So imagine that this very simple example with the Grover algorithm cannot be executed properly, meaning that all the theoretical quantum algorithms are not executed. I mean, cannot be executed nowadays. That's why variational algorithms like the variational quantum eigensolver or in quantum machine learning are happening, because in the variational quantum algorithm, for example, only uses 1 qubit or 2 qubits maximum to calculate the eigenvalue of the hydrogen molecule. So this is a good way of measuring everything. Is this useful for us, the eigenvalue of the hydrogen molecule? No, because it's the simplest molecule in the world. This is super well studied and it's not enough, but at least there is a proof of concept on how to grow and how to use quantum computing and demonstrate that this technology works. Because remember what we spoke of the upper cycle of Gardner, etc. So we need to think that at the very beginning, 10 years ago, when I was speaking with people about quantum computing, everybody was saying, this is science fiction, this is impossible to work, quantum physics in computing, it's impossible, etc. So just demonstrating that this algorithm, the variational quantum algorithm works, it was useful for quantum computing, because we could demonstrate that was something that not now but in the future will give us a lot of value. Because now what you need to imagine is that you need to be a strategist, and you need to imagine that now it's not giving value to business, but in the future will be. Sorry. So this is the aim, okay? Questions right here? I don't think so, right? I think it's simple, correct? Okay. One very important aspect that I didn't say about the quantum Grover, about the Grover's algorithm, is that this needs to be repeated n times. Okay, it says now here square to n, that's correct, but what I'm saying is if we want that and this n times that the Grover algorithm needs to be repeated, needs to be calculated previously, and of course it can be calculated previously theoretically. Like for example here, the Grover's algorithm, okay, works, what am I saying? Okay, the Grover's algorithm works in that case theoretically. If we do the maths and we calculate theoretically how many times the diffusion operator needs to be repeated, the solution is 1. That's why we get the correct answer. But if we don't execute that, if we would execute the Grover's algorithm twice, we repeat it twice before we measure, we wouldn't get the expected solution. We're going to see that. But one very important aspect that I didn't see is that the Grover algorithms needs to be repeated n times, and these n times can be calculated theoretically. Okay, now let's see. We have all of this, but of course, it's not well established. But Qiskit and all providers allow us to have more encapsulated functions where we can execute that in a proper way. So let's go to do all of this with the encapsulated algorithm. We are going to do the same example as above, okay, 101 and 110, but with the encapsulated region. So first of all, we calculate theoretically with this, we can calculate with this, we can calculate how many times we need to repeat the Grover's algorithm. And in that case, it's just one, as I say. Okay. Then, very simple, the oracle is true that the oracle needs to be represented as the oracle needs to be represented with these functions, with the quantum circuit. Okay. I mean, we need to guess what is the circuit. How can we do that? If we don't know, we can do that with the how to construct an oracle class. As I said, we build a matrix. Once we have the matrix, we put the circuit and we have it. Okay, as we know previously, we just compute here and then we need to use the amplification problem, okay, class that is added to the Grover circuit. Okay, this is quite tricky. Sometimes I don't understand Qiskit, as Urbano said, Qiskit is evolving a lot and sometimes I don't understand. This is quite easy. We have the Grover, there is an object called Grover, awesome, and then with a function of this, with a function of this class, of this object, sorry, this is an object, with a function, there is a class called Grover, with a function of the class, put in the number of qubits and the solutions, we get the object, the iterations we have, awesome. Then we need to specify the oracle, awesome, okay? And then we have the Grover circuit that is going to be built based on this oracle and what are the elements that we are looking for. Okay, we need to put both of it. And then Grover is getting that in a more highlight way, meaning like a black box. So now we have stage 0, stage 1, stage 2 is the same like qubit 0, qubit 1, qubit 2, but like a black box. This is encapsulated. So now this is just the number of qubits, 0, 1, 2, 3 number of qubits. And then we have from the Grover, because with this class, what we are getting from this class is an object that has different functions of the Grover circuit. And it has all the information of the future Grover circuit. Okay? Then we have now the number of qubits. This is the oracle plus the initialization. This is the beginning of the Grover circuit, meaning that in this encapsulated, we are getting these two parts together. Okay? And we are also, I think, the Grover operator. Okay? And, okay, we are having as well the diffusion operator. Okay. This is the encapsulated algorithm, meaning that this amplification problem is having the whole circuit inside of it. Okay? As this is something well established theoretically, that is always repeated as many qubits as we have, okay? This is already well established as many qubits as we have. This amplification is going to be the whole Grover circuit, where from this object we can extract all the information we need. That's why in this amplification problem we need to insert by ourselves the oracle. Why? Because Qiskit is giving us a tool. This tool from Qiskit is helping us to get the circuit. But as I said, for example, in the challenge that that IBM released a lot of years ago, like 7 years ago, where I told you the Spanish student, the doctor, the Spanish student won by understanding that the matrix was diagonalized and he reduced a lot the circuit depth. We could also to get a better oracle with a shallower circuit that better than the tool from Qiskit. Okay, today is very, very difficult because we are getting better, bigger matrices, and it's very difficult. And Qiskit improves quite a lot the transpile function and all the functions that allow us to get the circuit with GenAI and discriminative AI, with reinforcement learning and GenAI. So it's very difficult, but we could introduce here the oracle. And finally, we are telling them the elements that we want to select. Okay, what are the elements that we want to get? Okay, so finally, but here is the whole circuit that is represented here just like a black box. Okay, so we put that here, we put etc., and now we execute, we amplify, meaning that amplify is this part of the diffusion operator. That's why this is called amplification as well. Okay, we amplify, and finally we get the result that is true, and finally we execute, and we get the two options that we want, 110 and 101, 110. Why am I putting this here? Because as I told you, the Grover algorithm needs to be repeated n times. If you do that with the encapsulated Grover algorithm, okay, if you do that with the encapsulated Grover algorithm, everything is fine. You don't have any problem and everything is fine. Why? Because it already repeats the diffusion operator the times that are needed for the purpose. But imagine that you are programming the Grover operator by yourself. And so imagine, unfortunately, you compute the theoretical formula of this, you compute it wrongly. So instead of repeating it, for example, imagine that the good one is 3 and you compute and it's 2, so you get it. So this function right here is a way to demonstrate, to know whether the result is successful or not. So if it gives you false, it means that you or repeat more or repeat less the diffusion operator than the theoretical formula tells you. Okay? And now we are here. Okay, 23. Good. Okay. So till here, any question? Is there any question? No? Is it clear? I think it's clear, right? But is there any question? Because maybe I'm speaking like before not correctly or something that's not correct. Do you understand it?
All good, Alberto.
No,
Thank you very
yeah.
much, Marta. Okay, perfect. Then let's go for the applications. And this is here where I want you to program. Okay? I'm going to start introducing some knowledge that is not necessary for this subject, but I want you to have this and it's going to be part of the deliverable because I want you to have this problem. Okay. And I'm going to go very fast, but um, in quantum computing, basically, there are two main areas of application in the NISQ era, in the noisy intermediate scale quantum computers. One is quantum machine learning, and the other one is optimization. In optimization, operation research area, you can have or linear regression models. What it means is that you have variables that are linear, 0, 1, 2, 3, 4, 5. And you can have different multiple models inside operation research. You can have inequalities, etc. But in quantum computing, what we are using here is a quadratic and constrained binary optimization problem. Kubo formulation. You will know a lot about this when you finish the master, okay? I mean, the entire subject of 812, adiabatic quantum computing, is related to that. So no worries because you will know a lot and you will learn a lot, okay? But now I'm introducing you that the Grover algorithm can be executed as one of the applications of the Grover algorithm is also an optimizer. And an optimizer that solves a Kubo function, a quadratic and constrained binary optimization Kubo function. Okay? Very simply. How does it work? Very, very simply and very fast because I want you to program. Wait. Imagine then Urbano and myself are we are not fighting, challenging, no. I don't know. Today I'm very vicious. Well, we are playing. Urbano and myself are playing, okay? Alberto, Urbano. And basically by flipping a coin. And the fact is, we need to flip both the coin, and when the result is different, but I get the head of the coin, I win. Otherwise, I lose. But if Urbano get the head of the coin and is different from mine, I gain. Okay. So we have the head and the tail of the coin. Okay. So I get the head and Urbano the tail. So I win. I get the head and Urbano head. No one's win. I get the tail, and Urbano the head. Urbano wins. I get the head and Urbano the tail and Urbano the tail. No one's win. Okay? This is a combinatorial problem, right? This is how quadratic and constrained binary optimization works. Now we have here two variables. X1 it's Alberto and X2 is Urbano. And then if all of this happens, and then what we have now is a cubo, such a way that we have x1, x1 1 plus x1 2 plus x2 1 plus x2 2. Okay, so this is like a matrix. These are the diagonal. This is like a matrix. These are the diagonal elements, while these are the other elements. Okay, and this is how a structure is 1 0 1 Alberto, etc. I mean, I don't want to explain further. I just want to give you a quick overview of what a cubo formulation is, okay, and how this is expressed. You will see a lot of this. Everything will make sense, okay. If you have any questions, of course, now ask me. But what I want you to show you is that this is an optimization problem on optimizer, and the Grover algorithm is used to help this optimizer, okay. We have here different elements. This also can be written as follows, okay? Because this is because as I express x1 x1 plus x1 x2, sorry, plus x2 x1 plus x2 x2 was the fact that all of these elements are binary elements, okay? And these binary elements means that x belongs to 0 or 1, and x belongs to 0 or 1, and x squared is equal to x, right? Because 0 to 2, 0, 1 to 2, 1. That's why x1 can be expressed like x1 plus x1 x2 plus x2 x1 plus x2, because this is x2 squared that is equal to x2, and this is x2 squared 1 that is equal to x1. And this combinatorial problem that I described right here can be written as mm, x1 x2 x1 x2 x1 0 x2 0. So this combinatorial problem You can see, right? 2, 2, 2, 2, and this is x1 plus x2, and this is equal to the cubo. Okay? And we want usually is to maximize or minimize this. Okay? If, for example, instead of plus, what I would put here is minus. Because maximizing means that Alberto wins. So maximizing this, what would be? 1, right? X1 is equal to 1 if we maximize. And if we want to minimize, x2 is equal to 1 and Urbano wins. Do you follow me or too much? Tell me, please. Hello? Hello?
Uh, hi. Trying to think about this. So I'm not sure I understand the relationship between the equations on the right to the table on the left.
No, there is
If
no
that makes sense.
there is no relationship. No.
Okay, so that's good. So that's great. Thank you.
Okay. Do you understand then, Urbano? Yes, right? Marta and Raúl,
Yeah.
do you understand?
Yes.
I think so, the idea, yeah.
I really like you. Fucking smart. You are so fucking smart. Awesome. Then let's go. Then you understand more or less from a combinatorial problem now very quickly how to translate into a cubo, that is a quadratic and constrained binary optimization problem. Okay? Then you know now how to express that, right? Then, yeah, blah, blah, blah. Yes, okay. Then the grovers, as we explained at the very beginning, grover can be used as an associative memory or, for example, an optimizer. Like an associative memory is application that can has algorithms like a neural network or Grover. Grover can be used as application or an optimizer. Okay, so here we use keystate optimization to build the quadratic cubo. This cubo over here, okay, that is right here. So we use it and we get this exact cubed minus 2x0 minus 2x0 plus 3x1 plus minus 14 divided by 2 in the non-linear terms. It always put like that, okay? And then we have this quadratic constraint with the bounds of 0, 1, meaning that the variables are binary. And this is the constraints because this is Cplex, okay? Cplex. Qiskit is from IBM. IBM uses Cplex as the language for optimization. So we get this. And then we execute. What do you think? When we always execute with the Grover optimizer, we are always minimizing the function. Question because it's important for the deliverable. If we want to maximize this equation, yes, if we want to maximize this equation, what do we need to do for maximizing this equation?
Okay, multiply it by -1.
Correct, Urbano. 1 point for you or 10 point for you. Correct. We multiply by -1 the whole equation, and that's it. Do you know why?
Because you're inverting the convexity to a
Yes.
concave function or something like that, right?
Yeah, you're correct. But I'm going to express you more simple way. 1 second. I'm going for a pen. Okay. we have this function x squared. Can you see my screen? I would say. Can you see the paper?
Yes.
Okay. We want to maximize, right? And we want to minimize. And if we want to maximize this, what do we do? Well, sorry. Okay, we have this function. If we want to minimize, we will get this. If we want to maximize, we want get this, right? But as we have an algorithm, the Grover optimizer does only minimization. If we want to minimize, we multiply by minus one. What does the minus one does? This. This is exactly what it does. That's why we get the maximum here. Because when we multiply by minus one, we did this. We multiply by minus one, a function, we do this. Multiply by minus one, a function, we do this. It's a projector that changes the sign of the function. Okay? I know it's very simple, but this is a very good way to remember why this is useful. Okay? And then if we want to minimize this function, what are we going to get? We should get x0 is 1 and x1 is 1, correct? So we get minus 9 plus 3 is minus 6. So let's do that. And correct. 1, 1 and minus 6. Okay? And that's it for today. I wanted you to program, but I think we are not going to be able because what do you prefer? You program another example of this, or should I explain the HHL algorithm? What do you prefer?
I think the HHL.
Yes.
Yeah, same here.
Okay. HHL. One very important aspect. You are not going to program this, okay? This is the HHL algorithm. I'm going to explain the HHL algorithm, okay? But this is from an old QCT version. And in fact, since QCT was updated, since QCT was updated, it didn't update the HHL algorithm. So this is just for learning purposes, okay? But you can omit the rest of all of this. What I'm going to do is explaining how the algorithm works, but as you can see, it's too long for a very simple problem where we know the solution. That the problem is this. Two different equations, 1, 0, is x plus minus y divided by 3 is equal to 1 and minus x divided by 3 plus y is equal to 0. And all of this is prepared to have an state and a very state that we know the solution, okay? And see how deep it is when we decompose in elementary gates. Okay, I mean in imaginable, and of course we also need a processing of the information to get the right solution, etc. Okay, got it? Okay. Did you see the HHL algorithm also in the quantum algorithm class and you understand it?
Yeah, we saw it.
And do you understand it? How it works? Or do you just saw in a high level?
Yeah, we did some exercise on it.
Yeah,
Yeah, you
it was
did.
quite detailed.
Yeah.
We also used the Streelab. I think it was called the program.
Which one?
Streelab?
I don't know. I need to talk to the professor. Okay, then you know how it works, right? That the quantum phase estimation algorithm is work here, etc., right? Because if you did
Yes.
exercises, okay,
Yep.
cool. Then then I will explain it. But if you already know about it, I think it's okay because before it's true that I was showing how it was expressed and how to express the solution, etc. But yeah, I mean now it's not useful at all. I mean, and it's not useful for an application or whatever, as you can see here. I mean, you need to count 1, 2, 3, 4, 5, 6, blah 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 blah. 1, 2, 3, 4, 5, 6, 7, multiple layers. Okay, I mean it's too long. As you know, if you well know, I won't explain further. You know that here you have, there is one ancillary qubit, this one over here. There is one ancillary qubit, and then there are three quantum systems. where here we have the control qubit, and here we have the two target qubits. Okay? We load B, that is independent, in the control qubit and one of the two target qubits. We load B. Then we use the quantum phase estimation algorithm of this oracle for finally the eigenvalue reversion. And you know that you need to be measuring this ancillary qubit till you get one, right? And once you get one, is when you reverse the algorithm, you use the dagger on the quantum phase estimation algorithm, and finally you apply a post-processing to finally get the solution. Where the solution is not what you expect from X and X2. The solution is something where you finally need to do a post-processing of the information and then you will get it. Okay? I mean, I just wanted to explain, but being very honest. So we have 15 minutes or so. So what I want you is to start programming then rather than explaining the HHL. Likewise, and as I went very fast this class, I will put you class of last year. Probably, I don't know, I need to see. But yeah, okay. For me, the main purpose of this class, you will have two deliverables from the Grovers. One is a Grover optimizer and another is with the encapsulated algorithm. Work with it. You will have the Jupyter notebook and it will be very simple. Okay. But yeah, I mean, but for me, what is very important from this class is one, you understand the Grover algorithm. Secondly, you understand the different parts of the Grover algorithm and how to implement them. Okay, and finally, you know the applications of the Grover algorithm and how it works in a structured database, like the associative memory or the optimizer. But most important, the associative memory, because this is how the searches of the Grover algorithm works in a structured database. Okay. Okay. Then with that
Okay.
said, let's start programming. We're going to do an exercise, very simple exercise, but let's do it. Let's program this over here. Okay, write this down, please, in a paper. Okay, do you have it?
Yes.
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 Okay, then I'm going to put you this over here so you are like that. Okay, then maximize this Kubo function with the Grover algorithm. And you have, yeah, it's not much, 10 minutes, a bit more. Maximizing this, okay? I mean, you can see the solution by eye, but I want you to program this. Okay, and call me in a second. How are you doing, students? Do you achieve the expected result? Hello? Yeah, you're still here. Do you get what you expected?
Yep.
Yeah, cool. I mean, the key fact here on what I show here is this 13. Okay? Be careful because at the end, even in adiabatic computing, the single element is not introduced in the solution. So most of the times the f-val gives you the correct solution, but you are not adding the single element. So that's why you don't get what the really answer is. It just the tricky part of this is this one, just to be aware from your side. Okay. Okay, cool students. I'm so sorry, but I need to leave for today. But we explained everything, so I'm happy in that case. Lastly, do you have any questions or something that you would like to ask me?
Yeah, I was just curious, is there any intuition why Grover can be written as an optimizer? Because I mean, it seems, I mean, if you think about it, it seems like two different problems, right? One is optimizing the value of a function, the other one is finding solution, finding, something on an unstructured database. So I was just curious if
No,
there's
it's the
any
same.
intuition.
It's the same. It's the same. No, sorry, sorry, I didn't understand your question. Could you repeat, please, Urbano?
Yeah, no, it's exactly this is if there's an intuition to understand why. I mean, in one case, you are finding something in a structured database, which is how we think about Grover, right? And the other one is
Mm.
actually you have a function that there's a minimum, right? But the minimum is not necessary. You don't know what the minimum is, right? Differently from probably, I mean, the case of Grover, you know what thing you are looking for there in the database. I was just trying to think if there's a way to understand how we can go from one to the other. I mean,
Because
kind
it,
of an intuition
because
that's
it's the
high
same.
level.
Because it's the same, just it's the same problem. It's solving the same problems. You have different elements, in that case x1 and x2, and what you want to know is what of this element is giving you the minimization. So you have elements there that are not labeled, and what you want to know is which of these elements is giving you the minimization. You don't know the eigenvalue, but you know what are the elements you want to look for. That is the ones that minimize the solution.
Oh,
What
okay.
I mean? I mean,
Okay.
this is the way of thinking. You have
I see.
a combinatorial problem with multiple elements, and all of these multiple elements are in the structured database. You know what are the elements that you want to look for, that are all of them, and then you want to minimize this, and this is how you get it. So at the end, it's minimizing a function, but in this way, the Grover is looking for the elements of this unstructured database to get that.
Okay. Okay. Thank you. Thank you,
You're
Alberto.
welcome, please. Urbano, all you need. Anything else, students? No?
Not right now. Thank you.
Okay, cool. Then thank you very much for attending these classes. I'm super happy, really super happy. Thank you very much for attending and all. Marta, I see you unmute. Is because you want to ask a question or something?
No, no, no. I was ready to say thank you, Alberto.
Okay, cool. Then what I was saying is thank you very much. I really appreciate that you joined the classes. It was very happy because moreover you were answering all questions, so it was awesome. So thank you very much, and keep in touch. Anything you need or whatever, as you know, instead of asking me for money, I will always be here for you. Okay. So thank you very much. I'm going to stop recording.